Hello, everybody, and welcome to the MANTEL Symposium. My name is Mike Thayne. I'm a researcher at the Leibniz Institute of Freshwater Ecology and Inland Fisheries in Berlin, Germany. I've been there for 3 years trying to determine critical thresholds for lake ecosystem resilience as observed from long-term high-frequency data. To put this into context, I've been exploring how extreme wind events of different duration, frequency, and intensity, and how they affect the resistance and resilience of lake ecosystems. If we just jump right into it, a recent review paper by Stockwell et al. In 2020 gives us a very good overview of some pathways of how storms can affect lakes. If we start at the top of the diagram, we see our primary storm characteristics: direction, frequency, intensity, duration, and timing. And I would say there's a sixth one, and it's in the title there with storm, which is rain. Now, if we follow the pathway down the diagram, we can see that the storms simultaneously affect both lake characteristics and the watershed that's influencing those characteristics. And depending on those characteristics, the lake can affect the pre-disturbance conditions of the lake depending on those characteristics. So, for example, the storm can change nutrient and sediment loading. It can also affect residence times, light conditions, the mixed layer depth. In shallow lakes, sediment resuspension can happen, and it can break down stratification. The storm effects on these lake conditions then have a cascade effect through the system. For example, imagine a sediment resuspension event occurs and you are a foraging fish that site feeds on zooplankton. The increased sediment in the water column most likely decreases your ability to feed, therefore your survivability. And as this sediment stays in the water column for multiple days, so decreases your survivability. So on the other hand, we could be plankton in the lake, and perhaps nutrient and sediment loading and changes in light conditions occur. Maybe this affects your ability to uptake nutrients. Maybe it helps you, maybe it doesn't. Maybe you are adapted to shady environments, maybe you're not. So depending on your adaptability, you could be affected in different ways. And finally, if we follow the diagram to the bottom, the storm can finally affect the ecosystem as a whole. And things like biomass production start to be affected. So the storm can break down or form algal blooms. Perhaps it'll start to affect carbon sequestration. And finally, the focus of my paper, or my presentation today, is this topic of resilience. You'll hear throughout the presentation me use both the terms resistance and resilience, which will become more clear later. If we use this diagram, though, it's a perfect way to introduce the topic of my research at the moment. And as I said, I'm focused on this idea of resistance and resilience, and we quantified resistance and resilience in a group of response variables. We grouped them into a group of physiochemical variables and a group of biological variables. And we asked the question, we hypothesized that antecedent lake conditions are more important than storm characteristics in determining the resistance and the resilience of a lake. And the antecedent lake conditions that we considered are there on the right. And the storm characteristics, we considered all of those, plus precipitation, and we gave particular focus in this research on this idea of fetch. And in my current research, I'm looking at other lakes of different depth characteristics, but this paper is centered around Müggelsee, which is a shallow polymictic lake with an average depth of 5 meters. Now that we have an idea of what we're going to be looking at today, I think it's appropriate to get an understanding of resistance and resilience. And the best way to do this is with this conceptual figure. And here we have time on the x-axis, and on the y-axis we have some ecosystem property. You can imagine water temperature or chlorophyll, whatever is easiest. We see that the ecosystem property is oscillating quite nicely and then is disturbed. In our case, is disturbed by wind. If we follow the blue path, we see that it responds quite abruptly, but then returns to those pre-disturbance conditions. If we follow the red line, that would be an example of low resistance and high resilience. So if we follow the red line, it follows a similar path but does not return. This would be an example of low resistance and low resilience. So resistance and resilience is then the lake's ability to resist change in the face of a disturbance, and resilience is then its ability to recover to pre-disturbance conditions. And as you can see, you can have a gradient in those responses. And so now what resistance and resilience is, I would like to give you an overview of how we went about analyzing storm effects on resistance and resilience. And the first thing that needs to happen is a storm needs to blow over and affect the antecedent lake conditions of the lake. The next thing is to then identify those storms. And we did this in Müggelsee by transforming wind speed into shear stress and inputting it into a general extreme distribution model. Don't try and make sense of these figures, as I will make, you'll see them bigger in just a moment. This step gives us a nice threshold to then apply to the time series, which gives us our storm events to then quantify resistance and resilience of each of our response variables. The result of this is an indices of resistance and resilience for each one of our response variables. It's nice to quantify storm responses into indices because you're able to standardize across both variable type and later for comparing with different lake ecosystems. So then we can take this and answer our question about storm characteristics and antecedent lake conditions by inputting them into a boosted regression tree model as predictors, where the response is then the indice values of each of our response variables. And this gives us the relative importance and marginal effects of each one of our storm characteristics and antecedent lake conditions and their effects on resistance and resilience. So the primary result of the general extreme distribution model is the figure on the top left here. And basically what it gives you is that it shows you we looked at storms that are estimated to occur in the system every 100 days or more. Or if it makes more sense, we looked at those storms that generated wind speeds of 21 meters per second or more, which corresponds to a shear stress level of 0.93 newtons per meter squared. Now, if we apply that threshold to our time series in Müggelsee, that resulted in 25 extreme wind events that occurred between 2002 and 2017 and across the seasonal spectrum between March and October. So the next thing we have to do is quantify resistance and resilience. I won't spend much time here. As I said, we use functions that put these values into indices. The two primary terms in these functions is d naught, which is for calculating resistance, which is the absolute difference between the peak in response, absolute difference in peak in response compared to the control conditions. And then dx is the absolute difference between our return level and the control conditions. And if we have a look at the figure here, our control conditions were the 3 days, the 3-day average of our response variable prior to the beginning of the event blocked out in the gray shaded area. And then you can see how we break down the storm event using those terms to calculate resistance and resilience. So this results in our index of resistance and resilience for each one of our response variables. And what you can see along the x-axis is our response variables, and on the y-axis is our index values. And if we allow 0 to be our focal point here, if we're looking at resistance in red, 0 represents 100% change. And now if we look at resilience in blue, 0 represents 0% recovery. So therefore, positive values of resilience are when the system property went back towards control conditions, and negative values, therefore, are when the system continued to drift away from control conditions. So now that we have our resistance and resilience values, we're able to answer our primary question of whether or not antecedent lake conditions or storm characteristics are the most important in determining resistance and resilience. And actually what we find out is that they are almost equal in determining resistance and resilience. Antecedent lake conditions at 53% and storm characteristics at 47%. If we go back to our little roadmap here, we found that the most important storm characteristic was wind direction, so therefore fetch, and followed by frequency and duration. And our most important lake conditions were, I highlight here, nutrient and sediment loading and sediment resuspension, as turbidity was our most important lake condition, which was followed by pH and conductivity. And I highlight land use here as conductivity underwent a step change as a result of old mine tailings entering into the catchment. So now we know which is more important. We can actually look at how these different conditions and storm characteristics affect the resistance and resilience of lake. And here we see a partial dependency plot of how turbidity was affecting the fitted lake ecosystem resistance and resilience. We use the term ecosystem here as the figure is considering all of our response variables. And what we see is that as turbidity increased in the lake, that resistance and resilience both decreased with increasing turbidity. So this gives you a nice idea of what the lake may have looked like just prior to being hit by the storm. How about our most important storm characteristic? And if we allow the wind rows here to be our key, we found that storms coming from the less frequent directions resulted in negative impacts on resistance and resilience. We suspect that because of the way sediment deposits in the lake, and so when storms come from those directions, the likelihood of a resuspension event is much greater. Now, I'm sure you're all wondering what a lake looks like under these circumstances, and in the picture we can see a lake, or Müggelsee, being hit by an extreme wind event in 2017, and the figure to the right you can see the peak in shear stress and the turbidity rising directly with it. So you can see that these have a really strong impact on the lake ecosystem. So with that said, I just want to summarize what we just saw. We found out that antecedent lake conditions and storm characteristics together shape the resistance and resilience of a shallow lake ecosystem, in this case Müggelsee in Berlin. And what I'm doing currently now is expanding this methodology and looking at different lakes of different depth and trophic state to see how those affect resistance and resilience. And finally, the next step for this research is to see how it all fits into long-term climate trends. Anyways, thank you for listening. I hope you enjoyed the presentation, and maybe I will see you later in the session. Goodbye.